Well, right. What we're referring to is when you say green jacket, that's a Masters championship or Masters champion in golf. So yeah, I kind of got my green jacket on today. That's why a golfer might understand that. Okay, a couple things that I wanted to look at and discuss is the idea of this chapter deals with heat. Okay, remember heat and temperature are two totally different things, and one of the best ways to look at that would be, for instance, excuse me. When you look at this last weekend, okay, so we have all this snow that falls down on, what was that, Wednesday night through Friday morning. We'll just use that as an example, okay? So, we'll just use late Thursday afternoon when it quits snowing. Let's say, for instance, you look at your thermometer and it says 30 degrees, but yet you look on your sidewalk and the snow is melting. But what do we know about snow? It's water in the form of what? A solid. So typically we associate solid water changing forms at what temperature? At 32. So why is that possible? You look at the thermometer, it says 30, but yet this is melting. You're close, really close. Remember, to me the best way to look at that is when you look at a thermometer, whether it's in here or whether it's your house and it says 30 degrees, okay? That is an average amount of heat, okay? That means you're walking around the air. That is the average amount of heat that you feel with your hands, with your face, whatever. But when you're talking about the sun's rays shining down on that concrete, you'll say your driveway, asphalt road, or the sidewalk, what is that sidewalk or driveway or asphalt road doing with those sun's rays? Well, it absorbs it and then it gives off in the form of thermal energy. So even though the temperature says 30 degrees, that's just an average amount. There's still enough thermal energy to melt snow at 30 degrees, even though common sense tells you that, hey, wait a minute, this isn't supposed to melt until we see this, correct? 32. Okay, so my main point is, remember, heat and temperature, they're related. Okay, the temperature you read off of a thermometer or whatever it is, a device that spits out a number. That's not the amount of heat that's actually present. It's just an average account. That's why it's warmer down on the concrete than what it is up in the air. It's an average of those two together. Make sense? Clear? Clear as mud? Sure is. Okay. I like that. Sure is. That's confidence there. Okay. So when we do things like, let's see if we can hit this on the head here. Okay. Let's see here. Joules per gram degree. Okay. We want to make predictions here. Okay. So when we look at this substance, water, okay, that says triangle or heat of fusion, gives you that number, which is what? Joules. Well, that number, 40.7. Okay, so again, we want to make some predictions here. Okay, so keep in mind, this is one of the things you're going to have to do. Now, I didn't have time to review this because I was thinking you were still going to be in the gym cleaning things up. So, but that's fine. So we still have things to do. So you had correctly said 40. Now you don't need to write this down unless, let's see here, kilojoules per mole, because we'll be going over more examples. More often than not, you'll be given specific, this is a specific heat, okay? Or excuse me, not a specific heat, it's a heat of fusion. Okay, and there's also heat of vaporization, but in this case, that 40.7 was a heat of vaporization. Okay, so what that means is more commonly a heat of fusion or vaporization is given in joules per gram. Okay, now if we want something in joules per gram, which is a better way of looking at it, I think. Okay, we only had, we spent one day on this because you had smarter balance testing and you had prom building, and so the only thing that you'd seen that pertains to this chapter is this, correct? And then you also had seen okay. Okay, those are subscripts, the F and the V. That means heat of fusion and heat of vaporization. Now, what we did discuss, Q is a quantity of heat, it's energy. All energy is labeled in what? And this is something that you had wrote down, okay? So this is a mass, and that's measured in what? A specific heat is something that's measured in joules per gram degrees Celsius, and temperature is measured in degrees Celsius. So as we look at this label here, joules per gram, that must have something to do with an equation like this, or this. And it does. This here? It's labeled, it's a mass measured in grams. Okay? So notice you see Q 3 different times, and that is a heat. It's a heat in joules or kilojoules. Okay? That's all that means. Your mass is in grams. A specific heat, we had said, remember I had put a prosthetic bone, a scissors, and I can't remember what the other substance was on the table. Okay, so when we put those three things out there, which one do you not want to pick up if it's been sitting out there for over an hour and it's 85 degrees outside? Yeah, you do not want to pick up the metal because it does what? Conducts heat and electricity. It takes very little energy to raise this temperature. That's why it has such a low specific heat. This, however, would. Okay? It would take a lot more energy to raise this temperature to where it would actually start to get hot. Since this is a metal, we had wrote iron down. It had a specific heat of 0.444, I think is what we wrote down. Maybe yes, maybe no. It was up on the whiteboard. I do remember that at one time. Okay. So again, when we break some of this information down, this is just a temperature range, okay? It is the, remember the temperature final minus, yeah, so some of you have that. That's just a temperature range. That's all that means. A specific heat is just the rate or how much energy in joules, depending how big it is, the mass, and then the temperature range. That's all that means. Because if you look at the very specific definition of what specific heat is, that's where it kind of starts to get lost in translation. So we try to make more common sense terms of that. So if you ask the author or any type of textbook, we talk about specific heat. It says the quantity of heat required to raise a unit mass of homogeneous material 1 Kelvin or 1 degree Celsius in a specified way given constant pressure and volume. The quantity of heat required to raise a unit per mass, okay? The quantity of heat required to raise whatever the temperature range is and how big it is, okay? The smaller this number is, the better it will conduct heat. Excuse me. And then here's just the mass of a substance, and then this is, again, just the amount of heat in joules, okay? So, when we look at these guys, this is still heat, so it's going to be measured in what? Still going to be labeled in joules or kilojoules. So it's any type of energy, okay? This mass is still going to be measured in grams, but these two, however, okay, a heat of fusion and a heat of vaporization, okay? Now, what we mean by that, okay, for the heat of vaporization, the heat required to vaporize 1 mole of a liquid is called the molar entropy, or heat of vaporization, okay? Heat of vaporization. That definition again, you could say the heat required to vaporize 1 mole of a liquid is called a molar heat of vaporization. Okay? So the amount of heat, remember, is labeled in joules because it's a type of energy. Don't get so hung up on these formulas thinking, oh my God, I need to know what a heat of vaporization is and what a heat of fusion is and what a specific heat is. Okay, just set that aside. Don't let that be too overwhelming. Okay, so remember we said we can make some certain predictions on this here. So, what substance was this here that you said 40.7? Water, okay? So what that means, okay, I want to say this is 2260, okay? We'll see how close that is. I think that is the heat of vaporization for ice, okay? Yes. Or, wait, whoa. I said for water. I'm sorry. So, should be 4.14 joules per... Hold that thought. I don't want to confuse you people. You're probably already getting that way already. Okay? You're already that confused when you walked in. Why is that? You haven't been in this class? Well, that's why it was a good thing we got those exams out of the way. Okay? Yeah, 2260. I was correct. Okay, so remember this is a known substance. So we're going to take 40.7. We're going to use dimensional analysis. Remember, that is a kilojoule per what? What does it tell you up there? Kilojoule per mole. Okay? So we're working our way from kilojoules per mole to joules per gram. So what that means is we want to get that number labeled in joules per gram. Okay? Hold that thought. Okay? So what would you want to convert first? The kilojoule to a joule, or get rid of the mole and get that to a gram? Okay, so you said the gram can come first, and that's fine. You can do this as long as it's a known substance, and it's water, okay? So we need to know what the molar mass of this known substance is, which we do. So if we want to get rid of this mole, if it's downstairs, how do we get rid of it in the next step? Upstairs. We put it upstairs, okay? So for every mole of water, you said you want to get that gram downstairs, and that's fine. What goes on the bottom then? Of what? Of water, which would be what? Okay, so what we have is these moles have now canceled, and we've got kilojoules per gram. But we don't want kilojoules per gram. We wanted joules per gram. So how do we get rid of that kilojoule? That's exactly what you got to do. So if a kilojoule is on top, okay, a joule, and then what goes on the bottom then? Grams? You got that already. Mole? No, I don't see moles over here. Okay, so a kilojoule. Now, what's bigger, a joule or a kilojoule? A kilojoule is much bigger. So that means how many joules are in that kilojoule? 1,000. Okay. So, if our prediction is correct, which we hope it is, 40,700. Well, it's probably a good idea just to multiply it out. Look at that prediction. What? I didn't see that up there. 2258. Wait, did you multiply it by 1,000? Yeah. Okay. So what this means is some of these heat effusions are heat of vaporizations. Some are given in kilojoules per mole. Okay? Other times it's given in joules per gram. Now, it's much easier to me, in my mind, to calculate the heat if it's given in joules per gram, as opposed to kilojoules per mole. Now, mean vice versa? Okay, let's hold that thought. We can do that. Okay. Now remember, these have to be known substances. You just can't pull these numbers out of the air. It has to be something that is known. So, yeah, you would have to know this right here. Yes. So if we went the other way, 334. So 334 joules per gram. Okay? So now the prediction that we're making is that in this case, for water, the heat of fusion, in other words, this is how much heat it would require to change this to steam, because you're vaporizing. Okay? So in other words, one of the kind of a really ingenious deal that Pampered Chef has when you're boiling water, rather than putting a solid lid on there, and chances are you have one of these, what would you put on top of a boiling pot rather than the lid? Because no, you got a boiling pot of water. If you put that lid on there and let it continue to boil, yeah, it's going to blow it off of there because you're building pressure inside of there. So one of the deals that you get it from Pampered Chef, chances are your parents have something that looks like this. It's a red type of deal like this, and in the center it's got a whole bunch of things that look like this. I don't know how many there are, but what this is, it's a movable flap. So as you're, and it's attached here in the center, and what that does is as that steam pressure builds up inside, those flaps move up and down. Yeah. So what you can do is set that on there so you don't have to worry about the pot boiling over. Okay. Otherwise, it goes over on the stove top and this sound from. What's that? Okay. So, but what happens? You can put your no, you can't. You could try to put your hand along the side of that pot. Obviously, you're not going to do that because it's very hot. The only place it would be hotter or more hot is if you took that lid off, because what's being released? Steam. Steam is hotter than boiling water, because hot water, boiling water is 212 degrees. Steam is probably somewhere around, let's say, 220, 225 degrees. It's hotter than boiling water because it's in the gas phase.
So what about when you open up like your oven?
Okay?
You know, like when it's like at like heat like that, what's coming out? Heat?
Air and heat, yeah. Because what's happening is all those air molecules are expanding.
And they're just getting bigger and bigger when you open
Yeah.
them. Yes.
Yeah, so what that does is it just continually circulates the heat inside it. Now, chances are there's some sort of vent in there so it doesn't go boom. That would be bad.
But it's like a hot tub. Is that steam coming off of it? I don't know what steam is. I do, but I'm trying to figure out.
No, that's not steam.
What is it? Like,
It just means that the best way to look at that is it's evaporation taking place. Right? In other words, it's dew points has something to do with that as well. Like during the cross country season, you run on the golf course, okay? You walk back here and we say wipe your shoes, not because of mud, because they're wet, but it has grass sticking to it, okay? Again, that has something to do with dew points and what you're referring to. A lot more science related in that. Okay, so we want to make this correlation. So about 6.01 kilojoules per mole. So we had went kilojoules per mole to joules per gram. Well, we should be able to go from joules per gram to kilojoules per mole. So these two should be equal to one another. So let's go ahead and try that by saying we've got 334 joules per what? Per what? Okay. So do you want to get to the kilojoule first or the mole first? Okay. So in order to do that, which one of these would you want to cancel out first? You need to get rid of that gram. Okay. So again, this is a known substance. It's water. So if grams is downstairs, how do we get rid of it in the next step? You have to put it on top. So what is the atomic mass for water, of course? Okay, and that's for every what? Mole. Okay, so we've accounted for the grams. Now we've got joules per mole, so we're not quite there yet. So how do we get rid of this joule then? Right, but you got to do it in the right proportion. Okay, so kilojoule goes on top, and what goes on the bottom? No. You already got your mole. No. You got to get rid of that joule. Right. 1,000 what? 1,000 joules. Now your joules are gone. Now you've got kilojoules per mole, and that's what you want. So take 334 times 18 and divide by 1,000. Correct. That's why this dimensional analysis is so important that we spend so much time on.
I got 6.02.
Okay? Pretty close to what our prediction was going to be, correct? So is that just, wow, you people are smart, or is it kind of like, well, and no one's going to deny that, but each one of these substances has a known heat of fusion, heat of vaporization, and specific heat. Okay? So, what this means is correct. Unless you're given, let's say, this unknown substance has a molar mass of 210 grams per mole.
But you gotta have a molar mass.
But you have to have a molar mass or else you can't do these. So when you look on here, this has all the elements on the periodic table. Okay, so as you go across the top, it says, okay, so it says atomic number, okay, atomic mass, melting point, boiling point, density, atomic radius, so all these, entropy of fusion, okay, so that entropy of fusion, when we had it up here, was Q equaled mass times H sub F, heat of fusion, okay? And again, that's the amount of energy it requires to melt that substance. Because if it's a heat of vaporization, then it's the amount of heat that we require to boil it, okay? So when you look at the smelting process for the factories in Pittsburgh, you're talking about a lot and lots of energy. Why would that be? Well, what's happening in the steel mills in Pittsburgh? Well, they're melting in basically what? Not that they're vaporizing iron, but they're certainly raising it to a high temperature because you got to get, which it gives off lots of heat.
Global warming.
No. Okay. Anyway, so for instance, let's try something like this. Let's see if I can create an example to try to put this to use. So hang on. Okay, now my computer's not responding.
When you're in class and you're just folding it all out.
Okay, so let's look at an example like this. Then that will be where we stop for today. Okay. So if palladium or PD has a heat of fusion palladium, okay? That's what I thought. I thought I'd misspelled this. Some people say, that's wrong! Okay, so okay, now, one of the things, again, when you read these problems, okay, it's important to look at, is there a glare on the board or what?
Yeah, it's just I don't understand what to do with.
Well, we haven't got that far yet.
Wait, that's I need to know now.
Well, then we could, is that better or worse?
Um,
That's worse.
it's fine. I like it.
Now? Okay. So it says how much heat. So we know what variable are we looking for when it says how much heat?
We're looking for H.
No. Q. Okay? So that's going to be measured in what? Or kilojoules. So do we see joules and kilojoules in this problem? Yes. So if palladium has a heat of fusion of 162 joules per gram, how much heat is needed to melt 790 grams of that substance? Okay? So it's not asking how much heat is required to raise this from 10 degrees centigrade to its melting point. It doesn't give you a temperature range, so you know you're not doing this. That eliminates this formula because it does not give you a temperature range. It also does not give you the specific heat. It only gives you the heat of fusion. Okay, so in order to do this, there's one of two ways you can look at it. Okay, to me, the best way is this, which would be anytime, I would say about 90% of the time, if you have something measured in grams, that's where you're going to start. And also, about 90% of the time or more, you're going to change it to moles. But only half of that is accurate here. We're starting with this, but we're not changing it to moles. There's no need to, okay? Because it's not measured in moles, and we're looking for which variable. You correctly said it about a minute ago. Q, which is measured in what? So we're looking for that variable. Okay, so if we start with 790 grams, I had to look at that for just a moment, okay? So we're only looking for joules. How do we get rid of that gram? But then we're changing it to moles, and we said we don't want to do that. Yes. No. It's a constant for this particular element given in the problem. Right. So that means what's got to go on the bottom in the second step? No. A gram. And then what goes on top? The 162. So that's measured in joules. So what happens to these grams? So when they cancel out, what are we left with? What did we want? Yeah, that's it. So I can't stress this enough. You've got to learn to figure out what is this question asking for. So when it's going to be measured in heat, you're looking for joules or kilojoules. Okay? So you're just multiplying the two. I just made this problem up on the fly, so it's one of them you're going to have to just punch out and just say that would be accurate. Okay, so there's only about a minute left. with everything that we've done, is something brand new. Hopefully it wasn't overwhelming. And if it's one of them things where you just don't start spitting out answers, you're probably going to be all right. All right? So we'll pick up with this tomorrow.